Hello everyone, that's the second video for chapter 8 and maybe it's a short video but we have to finish chapter 8 and we talked about the minor loss, major loss in the fully developed turbulent flow when you have a turbulent flow in the pipe. Okay, turbulence is still a question for science. There are many different papers and books about the turbulence, but the turbulence by itself is a chaos, and it's not understandable and how the flow going to move because it's going to be random. But if you take an average or somehow you can theoretically solve that, but there is not any exact solution for turbulent flow, and this still is the least understood areas in the fluid mechanics, okay, especially in the pipe. So we talk about the critical Reynolds number that after 2100 you will have, or 2000, 2000 or 2100, you will have a transition that start in transitional period, and then you have fully turbulent flow. So if you plot this time here, it's a time in second, and here is your Reynolds number, and it's 2000, 4000, and here is your velocity profile in the pipe. Then at first, when the Reynolds number is less than 20,000, 2000, then you have a laminar flow here. Okay, after that you have transitional period, and after that you have fully developed turbulent flow. Okay, these are the velocity profile, and you see you have noisy profile. That's because the velocity is not smooth, and the velocity is going to change. But there are some advantages and disadvantages with the fully or turbulent flows. Okay, at first you have to know that if the velocity comes in the laminar part, and it's one dimensional, so you have only u in x direction, and we talked about that in the previous class. So it's a laminar flow and you have velocity, but after that you have some wakes or something like vortex. So it has to be known that you have a u velocity, but at the same time you have v and w. So it's going to be random motion, is known as, is going to be 3D. That's one of the characteristics of turbulent flow. Turbulent flow is always 3D, so the flow is not only moving in one direction, even in the pipe it's going to move in the r direction, also theta, so it's going to be 3D. And also these are like vortex, or it's known as eddy motion. Okay, so what will happen when you have a vortex or eddy motion? One of the main things that happen is going to be mixing going to be high, so the flow layers is going to be mixed with each other. So then if you put one particles of the fluid and you track it, it's going to be have a chaos or random movement from layer to layer, right? It's not going to be smooth like laminar flow. And since you have a vortex, the size of vortex or wakes at first going to be high, like transitional, and then after that you will have very small noises because the size of vortex or eddies are going to be smaller and smaller, right? And it's going to be very small amount of size of the vortex that finally is going to dissipate your energy. So it's another source of for loss of energy in the pipe, right? So in the laminar you have a viscous effect, you find out what is the loss, right? But here in turbulent flow you have another loss because of the turbulence, right? That's the difference. In the turbulence by itself, by getting the layers on each other and random motion and vortex that you have in the turbulent flow, then you will have a dissipation of energy because of the turbulence. So if I write it down just for your information, that turbulence is not always bad. It has advantages and disadvantages, right? So advantages, it could be enhanced mixing. So when sometimes you need to mix, that's why when you are going to mix your coffee or with the cream, you need to put your make it a vortex there, and then a chaos there, and also turbulent flow, because that's going to increase your mixing. By itself is going to be smoothly, laminarly move, and mixing is very slow. Okay, so enhanced mixing, also enhanced mixing is going to improve your heat transfer. Right, it's not always bad, but it has disadvantages as well. Disadvantages, it could be the drag force. So for example, you have a ball and the flow comes in and the flow goes over it, and here you have wake. Because of the wake that you have behind of that, there is going to be turbulence flow here, and the drag over that is going to be increased. So increasing the drag is bad thing that you have to know about the turbulent flow. What else? The amount of energy required also increases. Why? Because you have dissipation of energy, right? More power or energy is required. Why? Because you have dissipation of energy, right? These are the advantages and disadvantages in the turbulent flow, and you have to know that the mixing and improving the heat transfer also because of the eddy motion, increasing the drag by itself is just based on the experiment, and because of the weights that we have, and also power and energy because you have dissipation of energy. Okay. What we are going to do here, we are going to find head loss in this type. Okay, so for now you had another equation that was 64 over Reynolds for friction factor that we talked about that in the previous class, and it was the friction factor that we found it out, and times L over D V squared over 2G. That would be your loss here, and if that's laminar, it's going to be 64 over Reynolds. So you did that and you found it out for laminar flow. Okay, but now it's a turbulent flow, so you cannot do that right now here and use that equation because that's for laminar, and now we have turbulent flow. So at first we make it changes in the head loss and make it two terms, which is the major and minor losses. Okay, we separate those because major loss is because of a viscous effect, that's the major loss, and minor loss is because of components in the components, configuration, and also the direction. So it means that if you have any valve or any elbow, if that's not a straight pipe, then you will have a minor loss because of those, right? So you have a major loss that is viscous effect. Again, this viscous effect is not the same as viscous effect that you have in the laminar flow. Okay, you will have by itself viscous effect is different here, but it's the same as definition that you have in laminar flow. So it's going to be the major loss that is for straight pipe. Okay, but if you have anything like valve or elbow or anything that is additionally going to decrease your energy or loss your energy, this is going to be another term that is going to be calculated. Okay. Excuse Okay, so we did that dimensional analysis in the laminar flow. If you check the notes and check the previous video, we write it down the parameters that the delta P or pressure drop is dependent to that. This was velocity, the diameter, the length, and also mu. Okay, but the difference is that in the turbulence, two additional terms should be added. In the laminar flow, the density, because you have eddy motion, you have inertia or the mass of the fluid, and also density is part of is another parameter that contribute in the loss and energy loss or pressure drop that you have. Okay, so we have added two additional parameters here. That one is rho, that is because of the turbulent flow, but the mu was before and it's because of laminar. Okay, so the difference is that epsilon and rho are two additional parameters that delta P or pressure drop is dependent to. Okay, so if you write it down as a tau, because you are talking about major loss, right? The tau is not minus mu du over dy. This was for laminar, right? Here in the turbulent, you have tau, which is tau laminar, plus another tau, which is for turbulent. It means that you have the same major loss that you have for the laminar flow, but additionally because of the chaos that you have. Okay, so laminar plus another additional tau or between the layers is also part of the pressure drop. Okay, so we'll list the parameters as Vd, mu, and L that we had before, 5 parameters. Additionally, 2 parameters, which is epsilon and rho. Rho is density that is comes and in the turbulence is affect the pressure drop, and also epsilon is roughness. Okay, so that means the roughness of the pipe is playing is not negligible. For the laminar flow, when the flow was laminar, it was stick to the wall of the pipe, and the roughness or smoothness of the pipe doesn't change that much the pressure drop. But in turbulence, it's going to be, the flow is dependent to how much roughness you have. Okay, because the roughness that you have, if you have high roughness, or roughness is high or smoothness is low, then the flow is going to be much more turbulent than in the pipe that you have very smooth shape, right? So these are also parameters that are going to come down here and play game. If you do the dimensional analysis and find the pi terms, now you don't have 3 pi terms, right? You had 2 pi terms before because you have 5 total terms and or variables minus 3 MLT, the 3 units, then you will have 2 pi terms. Here you have 1, 2, 3, 4, 5, 6, and 7 parameters, right? We listed here. We have 7 parameters. Again, minus 3 is going to be 4 pi groups, right? So finally, you have 4 pi groups here. If you do the dimensional analysis, you will find it out that is going to be one of those going to be Reynolds that we have before. Another one is going to be L over D that we had the same for the laminar flow. And here also delta P over 1 over 2 rho V squared, which is the non-dimensionals of the pressure drop. Again, we had that before. But here, because of 2 additional terms that we have also Reynolds and epsilon over D. That epsilon over D is your another term that is going to be relative roughness, is going to be relative roughness. Okay, these 2 terms also added. So in turbulent flow, delta P is not only dependent to the L over D. That was only L over D here, but now 2 additional pi terms are added. So if you assume that the proportional again the proportional is the pressure drop is linearly proportion of the pipe, then you can bring the L over D out, right? But L over D comes out, but still you have another function that you have to find it out. Then this is going to be a part that you have to find it for the turbulence. But if that was laminar, it was easy to find it out. If you're laminar, you have to replace L over D, the phi or function that was only constant there, right? It's going to be 64 over Reynolds. Then equation going to be delta P over 1 over 2 rho V squared is equal to 64 over Reynolds, which is your F or friction, times L over D, right? That was the equation that you had for laminar. But in the turbulence, you have to find out what is the phi, right? The equation. So it's going to be for turbulent flow. By doing the analysis, in the dimensional analysis, you find it out that is going to be the same L over D multiplied by another term, which is Reynolds, and also roughness is part of it. Okay, this is not only the Reynolds. It was before the Reynolds, right now is again epsilon is also added. Okay, so you will have it, but you have to know that what is this function is not coming from theoretical analysis, because we don't have any answer. As we know, the turbulence is not understandable totally, and we don't have any theoretical answer for that. So the answer for this phi bar, or phi hat, is from experiment. So it's experimental equation or function that is given to you, and you have to apply it to find the turbulence. So it's going to depend on different situation, and the Reynolds number is going to be different. So you will have a different chart or different thing to find it out. Okay. So for now, you have to know that this is not going to be theoretically answered by, or at least now, and also if you be in the higher level in the fluid mechanics, again there is not answer for that except experimental answer. Okay. So if you bring it here for the fully developed, okay, if that's a general form, right? That's a general form equation for pressure major loss. In general, you will have HL major. Major loss means that because of viscous effect. Okay, because of viscous effect, you have equation is going to be F friction factor times L over D times V squared over 2G, right? But this F by itself is going to be different for laminar or turbulent. So first you have to answer that question that based on the Reynolds number that you have, is the flow laminar or turbulent? Okay, if that's laminar, then F is going to be 64 over Reynolds, and if it's turbulent, you have to find out what is F. Where you can find it is going to be found by epsilon. At first you have to find that out the roughness of the pipe based on the different material that the pipe has, and also using the Moody chart to determine F. That's going to be, the Moody chart is the different materials, different Reynolds number and different roughness. It gives you a complex plot that experimentally is obtained, the result experimentally obtained, and fitted the function for that. So these are only reading for the from the table or from the plots. Okay, that's going to be the, that's going to actually is a given in the question. So it's not going to be a thing that you have to theoretically calculate that, because you don't have it. It's going to be different in different situations, because that's the turbulent. But in the laminar, you know that it's going to be 64 over Reynolds, right? So in general, your equation for major loss is going to be F L over D V squared over 2G. Okay, you have to say that, okay, if an equation given to you, and you apply the energy equation, okay, you have to know that the head loss should be calculated, okay, and you know that the head loss has two parts. One is minor. If it's straight, then you can say that is minor. the minor is going to be 0. It's only major loss. Okay. If it's not a straight, then minor should be calculated by another equation that we talk about here as KLV squared over 2G, right? But minor loss is only because of the valve and because of the not being a straight up in the pipe. It's not a straight, or you have elbow or any component that you have in the pipe. Okay, so that's a totally different thing. But in the viscous effect part, that is major loss, it depends that your flow is laminar or turbulent. If the flow is laminar, then the equation is also given. That's 64 over Reynolds times L over D times V squared over 2G. So F is going to be, your friction going to be 64 over Reynolds. But if it's not laminar, then the flow is turbulent. The minor loss still is going to be the KL V squared over 2G. That is the minor loss because of the valve, bends, or whatever that you have in the not a straight pipe. But the viscous effect is also should be read from Moody chart, or it also going to be a given in any question. Okay. In the final exam for this level, I will give you, if that's a turbulent flow, I will give you that what would be the F. Okay. No worry about it. The roughness and F friction factor would be given to you if the flow is turbulent, but you have to check that is it turbulent or laminar. Okay, if it's laminar, you have to use 64 over Reynolds, but if turbulent, you can use the constant numbers. Okay, that's the thing. But what about the minor losses? Each of those bending or valve or whatever you have in the pipe by itself add a loss to the flow and give you a pressure drop. Okay, so any valve, any bending, those all should be give you that how much is the coefficient or loss coefficient or KL. Okay, it has to be given, and then you can find what is the loss, minor loss for that. So in energy equation, you have to find that the HL is equal to HL major, that it has to be there. If the question tell you that the minor loss is going to be negligible, then you can neglect this part, but maybe KL for different things that you have in the pipe is given. Then you have to say that, okay, HL for minor loss, that is for the valve, based on the KL that it has. Again, HL for the minor, for the bending, if the given HL is KL is provided, plus whatever that you have in the pipe. Okay, so in total, these are going to be your HL minor, and the major is from only calculate for the viscous effect, and by itself is again coming back to see that it's laminar or not laminar. What else? We talk about that. We are talking about here in this chapter. We talk about pipe flow. That in the pipe flow, all about the round or circular shape pipe. If it's not circular, you saw that you have always used D as a parameter. D is the diameter of the pipe. Okay. What is not diameter of the pipe is actually characteristic length or hydraulic diameter in the pipe. If it's dark or whatever it is, but it's a conduit and it's closed and your wall is closed and the flow passes through it, but it's not circular shape, it's maybe rectangular or other type of the shapes, so the flow comes passing here with the velocity. Whatever you find and all the equation that you have found here in this chapter is valid also for this type of the ducts, as long as that you replace D with DH or hydraulic diameter. That the hydraulic diameter is 4 times area over perimeter of that, right? So for non-circular pipes, you can find that the DH, for example, DH is going to be 4 area, cross-section area over the perimeter of that, okay? For example, if we calculate that for the circular pipe, that 4 times AC is going to be pi D squared over 4 times P, which is 2 pi R, right? R is going to be D over 2, right? Or pi D. So the perimeter of a circular shape or circle is going to be pi D. So I will replace that with pi D. What would be left? 4 is going to cancel out by 4. Pi cancel out with pi, and one of the d's goes out. So the hydraulic diameter, that's why we only have d, or diameter of the pipe, in all the equations, because the hydraulic diameter for a pipe, a circular shape, is the diameter of the pipe. But if it's not the pipe, it's a duct, you can replace all the d's that you have in the equation by the dh of the hydraulic diameter for non-circular shape. Okay, that's the only thing that you can update all the equations whenever you don't have a circular shape pipe or a duct flow. And what else you have to know about this chapter for solving any question? That you have multiple pipes. If you have a single pipe, then you can say that, okay, so I have a pressure drop because it's a single pipe. Single pipe means that from input to output of that, nothing going to change, like the diameter. Physically, it doesn't change. Okay, so fluid is absolutely the same fluid because it's passing over that, but the diameter is going to be different. When the diameter changes or Q changes, then you can say that, okay, so the velocity change, the Q change, and also the diameter change. All of these parameters affect the pressure drop, so you cannot assume that this is only single pipe and check input and output and apply the conservation of energy, or HL major or HL minor for each of those. This is going to be different because you have multiple pipe or system of pipes. For example, if the three pipes here, you can see pipe with different diameter 1, diameter 2, and diameter 3 are connected to each other. So the diameter changes here. Okay, so it's going to be pipe 1, pipe 2, and pipe 3. In this type, the Q that passes over this pipe because of conservation of mass is going to be the same that Q is going to pass over it and Q that pass over that, right? That's going to be in electrical engineering going to be 3 wires that you have different I don't know what's the name of that, but it means that you have the same ampere or the amount of flux of the electricity is going to pass over it, but you have a different temperature because of the friction that you have. Okay, this is the same, but the Q is still the same because it's going to be conservation of mass or conservation of energy or whatever you have in the electrical engineering. So Q1 is going to be Q2, is going to be Q3, and it's going to be Q total, right? But the losses, what about the losses? The losses from H in loss from A to B is going to be equal to plus number 1 plus the loss in part 2 plus the loss in part 3. Okay? You have to sum up these losses, and it's not going to be only one of those. So you're going to have a loss for the part of the first part of the pipe, and then the second part also apply its loss, and the third part is going to apply the third part. So in the next video, in the example question, I will solve a question for you that we use a syringe that has 2 different pipes, or not a single pipe, is 2 pipes connected to each other with different diameters. Then we will find out what is the loss or head loss for part A and part 2, or 2 pipes. Okay, if you have this system of the pipes, then you can see that the flow has Q1, Q2, Q3, that these are different pipes with different diameters, right? So in this one, you can say that the Q total that passes over this system is going to be Q1 plus Q2 plus Q3. Okay, so this is going to be 3 velocities, 3 diameter, and Q1 could be different with Q2 and Q3, right? But the summation of all has to be your total Q that you have. What about the losses? If you have these 3, the flow that comes here to here should be the same situation, that because that's a steady state and the flow has the same situation and same velocity or direction, or whatever it's because that's at rest, right? The flow is the same condition that has here. So the loss that you have in the first pipe should be the same as second pipe and should be the same as third pipe. That's why from A to B, this is like energy. So energy of A to B is the difference is the same, right? The head loss is going to be the same. Doesn't matter the flow passes over A, part 1, or part B or part C, this should be have the same loss. Head loss is equal to part 1 is equal to 2 and is equal to 3. Okay, again it's that for different multiple pipes. For each pipe, again you have to use the equation that we provided for single pipe. Only we are talking about here that how you can solve complex shapes of the pipes when you have different shape of the pipes, and how you can use the equations and bring all together and have a more general form, right? Here also again is another question. So you can see from here A to point N, that is your node, you have single pipe, right? So Q1 is going to split it in two parts. At first you have to know that Q1 is equal to Q2 plus Q3, right? Because it's coming here and in this one it's going to split. That's why Q2 plus Q3 equal to Q1. What about the losses? So it's total loss from A to B, okay, from A to B is equal to, first, this is going to be like in a row 1, so the first two pipes with different sizes. So it's going to be HL1, so from here to reach the node, and then to reach B you can come from this side or this side. Which side you choose doesn't matter, but one of those is enough to find HL2. So HL2 or HL3 could be used, but only one of these two is enough, because you are going to move from this point A to point B. From point A to here you don't have any loss, right? From point 1 to point N, which is your node, you have HL1 that is here, and you have Q1 that's split to 2 and 3. You have two lines after that, but whatever you, which way you use to do analysis, from this here to B or from here to here and here to B, doesn't matter, because from here to here you don't have any loss. So it's going to be HL from A to B is going to be 1 to N or HL1 plus one of these two, not both of them. Okay, only one of these two are going to be enough for you to solve finding the head loss in this type of question. So what we did here in this to finalize the chapter, so we find it out the turbulence is by itself has a different meaning and also different type of equation. So first we summarize that what is the meaning of turbulence flow and what is in the fully developed turbulent flow, what we have as advantages and disadvantages of that, and how the flow moves after laminar and transitional to when it's fully turbulent. Okay, then we find it out that we have a fully turbulent flow, that pressure drop is different than laminar flow. Okay, so we did the dimensional analysis the same that we did before, but by two additional parameters that the experiment shows that should be added to the turbulent flow. What was those? There were rho density and also epsilon, which is the roughness. So these two added to our dimensional analysis, and we found it out that delta P is dependent to, we have 4 non-dimensional groups, that 2 of those were from laminar flow, but Reynolds and epsilon over D are additional. So we split these two and summarize that in laminar, this is going to be your friction factor, and F in laminar was 64 over Reynolds. Only Reynolds was there and we found it out. But here in the turbulent, you need to experimentally find out what is the field. So we mentioned that if you, in this way, you will have a major loss, right? That's going to be a viscous effect that's going to be split at that different equation if that's laminar or is turbulent. And we found it out in laminar you will have equation, but for the turbulent you don't have it. So it means that it has to be a given F in the questions, or you can find it out in the Moody chart or in the book, or you Google it, you find out based on the roughness that you have and the density of the fluid or Reynolds number that connect all together. What would be your the friction factor if the flow is turbulent in that pipe? After that, we've talked about the minor losses that's not related to laminar or the flow by itself. It depends to the characteristic or component in the pipe or your system of the pipes. That if you have a bending valve or whatever you have in the pipe that may add losses, this is going to be the summation of all these going to be your minor losses. And minor losses equation is KLV squared over 2G. So KL is going to be your loss coefficient, and if you multiply by it, it also be given in the coefficients. It has to be given for valve or what components, any component that you have. Okay, then you will find that of minor losses added to major losses, you will have total loss or head loss in the energy equation. And also we talk about the dark flow, because that's going to be not only these equations are not valid only for pipe flow, as long as that you replace all those D terms that you have in the equation with the characteristic length, because the characteristic length in the pipe flow, if it's circular, is going to be D. That's why we use the D, but this actually is the characteristic length or hydraulic diameter that's going to be calculated by 4A over P. The P is the perimeter of the cross-section area, and A is area. And finally, we talk about the complex system of the pipe with different sizes and different combination of the pipe. So it's not again single pipe, it's going to be system of the pipe, but any system of the pipes is a connection of single pipes. So we found out that if these pipes are in a row, then you can say that the Q's are the same as Q total, but head loss is going to be summation of the head loss for each. Okay, and the second part we talk about that if those are in this shape or this category, then you can say that the Q's are going to be summation of all Q's, because the Q that passes over this complex shape or the complex of pipes or system of the pipes is going to be splitted between these three. So Q1 plus Q2 plus Q3 is going to be Q total that you have that passes over this pipe. But the head loss that you have in each of those is going to be the same. So whatever Q that passes over 1 or 2 or 3 is based on the loss that you have in these three pipes, in a way that finally you have the same loss. Okay, it's going to match itself, the flow going to match itself and decide that that's the nature of the fluid mechanics, that's going to decide that which side it has to go, how much of the fluid should pass from each of the pipes that finally has the same head loss at final from each of those. And in general, if you have combination of all these, you will have one part that is part 1 is connected to 2 that actually is 2 pipes in a row, the shape 1, if you pass over this line, or it's going to be the same over of the first one if you pass over the second line. But we show you that the Q1 from here to here is going to split it, so Q2 plus Q3 is going to be Q1. And also head loss, for finding head loss between A and D, you have to go through one of these two lines, because after point N and end of these two, the head loss is going to be the same because of the things that we talked about here in the parallel movement. Okay, that's the end of this class, and in the next class I will solve 2 questions for you and about the laminar flow, and I hope that you enjoyed this class and chapter 8, and you will need it for future work, and try to solve more questions by yourself and also work on the homeworks that would be helpful for you guys. Have a good one.